Welcome everyone, and today we're going to do something different from Bone Animations. Actually, this is the second recording today because I did a recording earlier this evening. Now I'm back home at 8. I'm done with karate. Now, you know what? I want to do one more video because I'm kind of ahead code-wise. And so I'm working on two different things. One is 3D animations, and now I'm also working on something that I'm probably not going to really show much, but there's going to be certain aspects of it that I think is important to kind of make videos about because certain things are very useful. And sometimes like this subject for this video is mouse recasting. I actually found setting up the recasting difficult. Certain pieces, I guess the way I was built fungi or the way I've come to understand it, it's a little different than how it's explained here. But this is a very popular article for explaining how recasting works. And the gist of it is that you have to go from 2D all the way back down to 3D world space. So here's the steps of how to get from 3D to 2D, and what you got to do is go backwards. So you're going to get at this point you're going to get the X and Y coordinates, and then you're going to convert it into normalized device space, which is the clipping value between -1 and 1. And remember, origin is the center. It's the clipping space because WebGL, all of WebGL doesn't exist within that's cube. That's only about 2 units big in all directions. And then you got a homogeneous clip space, which I'm not exactly sure what that is. That's, I guess, after you add your projection. I guess that's the part that gives depth. Actually gives you depth. Eye space. I think this is where the camera comes in. This is where we move everything to where we perceive where you currently are in the 3D world. And then you got your world spaces where actually everything begins. So that is the traversal that we need to do to do it. And it's actually not that hard. And there's two ways to go about it. I'm going to go through 2 ways. I'm going to go the popular way, which is this one. Like a lot of tutorials, and they kind of reference this article, and they kind of do it this way. And it took me a while to get this one working right. I got the second method working right, which came from Stack Overflow, and where this one actually explained things a little bit clearer to me, what made me understand more why the way I wanted this method to work wasn't working the way I wanted to, because I knew it, but I didn't take into consideration that when you add the projection matrix, you're creating a frustrum. I'm probably saying it wrong. Don't forget, English is not my first language. A frustrum. Does it have the word here so I can just see the word? No. Well, it basically creates this shape where everything's kind of bigger up close and everything smaller from a distance. So the way the first method works is that when you click on a mouse, you get the direction from the center point, from origin, from the actual beginning of the camera, at what direction you want to go. This method doesn't do it that way. You don't get a direction. You actually get the exact point in 3D space, in world space that you actually clicked on, and then by doing 2 different points, you do it twice. Like remember, it says that the cube clip space is like it exists between -1 and 1. So you're going to go from one side of the cube to the other side of the cube, which is -1 to 1, and you're going to get the exact same position, but on both sides of the frustrum. Okay, so this is a great illustration of how this really works. And I was having such a hard problem with this version that it was going straight where I wanted to, and not realizing that I wanted it to work this way but I was using the mathematics for this one. So now that I have an understanding of both, now I know what's going on. So this, I think, it took me several nights to figure to come with understanding. And there's something called here perspective divide, which this article says not to do, but you need to do it to produce this these 2 points on the two sides of the 3D world. So yeah, it's kind of funny. It depending on which way you do it, and he kind of explains it a little bit. Where is it? Oh my god. There, if I do a search for divide, I'll probably say it. There you go. Do not use the reverse perspective division here because this is array blah 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 blah. He says ignore the false prophets. So I took in consideration, okay, he must be right. But I have to take note to this one little part right here that says you only do this in special cases of points for certain special effects. I'm actually trying to create a certain effect because I actually want to visually see the ray. So, and on top of that, I'm dealing with points, not direction. So you definitely have to do perspective division, which is done here. But if this makes no sense to you, you'll see in code, which I have to do it in JavaScript in a different way. This is actually one of the things that actually makes this actually work. Without it, you would never get the proper points on the 2 sides of the frustrum. So now that I've pretty much kind of went through the 2 articles, and both are practically the same. You do have to go backwards, but you go backwards in slightly different ways. And one last thing that actually screwed me up is right here. It says inverse the view matrix. I was having problems with the mathematics because I was using the inverse local matrix that's part of the camera. If you remember the camera, we have the local matrix and we have inverse local matrix. Inverse local matrix is actually what we pass to the shader. So the inverse local matrix is our view matrix. So I was trying to inverse. So I was trying to use that inverse because it's like, oh well, it's already inverse. That's the one I need to use. I was wrong. The view matrix is inversed. The inverse of the view matrix is its true original local matrix. So once I started doing, when I switched the mathematics around, this started working correct a little better. I didn't get 100%, but this improved it once I realized that the inverse, I don't need to do an inversion because I already have the original view matrix, the real camera matrix in the object. So that's the one thing. Like if you see this and you decide to I'm just going to invert something, it's like, oh no, it's already, this is inverted. You got to use the original. If you don't have the original anymore, then you got to invert it back. You're just bringing it back to local space. So that's it. So let's start looking at some code. So this is the first method. So I'm just using our control camera and putting this on down override. So this when I click my mouse down to start panning the screen, I can basically create an array based on the mouse movement. So this is kind of a quick hack to kind of really prototype and really test out this functionality that I want to implement. So I'm just saving some basically shortcuts, aliases, because I really don't want to type all that out over and over again. So this part is where we convert our X and Y position. We basically do these 2 steps in one go. We convert view space down to normalized device space. We do that right here. Those 2 steps are done right there. this part is what we convert, I guess, to view space. And then we multiply it by 2 and subtract 1. That would take us to, I guess, normalize the device space. That's what I'm calling it. Yeah. So now you might notice the equation is backwards for y. The reason why is because of how the coordinate system works in the browser. In the browser, the origin is in the top left corner. So y gets bigger going in the downward direction. But GL treats y getting bigger going in the up direction. So mouse-wise, y gets bigger down. GL, y goes up in the up direction. So that's why it's inverted. So where this would probably, like, if the x was at the maximum width and I multiply it by 2, it should generate a value of 2, and I subtract 1, and that would create 1, which is the maximum number. If I was on the other end and this created a 0, times 2 would create 0, and this would then minus 1. 0 minus 1 would make negative 1. So this way is the two extremes for x. The same thing applies for y. So, like in this case, let's say if we're going to the maximum, so it's 1 times 2 equals 1. 1 minus 2 makes actually a minus 1. If I'm doing, yeah, it makes a minus 1 out of it. If it's the other way around, if this generates a 0, 0 times 2 equals 0, and it makes a 1. So it's flipped, which is exactly what I want, because the two y's are going in opposite directions. So by having this little minus here, ends up flipping the y's for us when we convert from the mouse coordinate system to, I guess, normalized device coordinates. The next step in the article mentions putting into like homogeneous clip coordinate space. I think this means you have a fourth component, which doesn't really mean much. And then we put in the z position, we mark -1 because that's the direction we kind of want to go at. So that's the direction that we want the ray to go, because we're clicking into the scene, and forward in our scene is actually is negative on the z-axis. So after that, we set up the camera. We start. It says the I camera coordinates. Actually, that's wrong. Is it? Yeah, I guess it's I space. To me, I don't like the idea of calling this I space because it's not the camera. This is really the projection, but I guess it makes sense because it's the projection. It makes things look far smaller as they're far away. So what we do is we set up an empty matrix, and then we take our camera projection matrix and we invert it, and then we multiply our clip space with our inverted projection. And these have to be 4 because our matrix is a 4x4. So the only way to multiply a matrix is with another matrix. And this is basically a matrix of 1x4. Where this is a 4x4, this is a 1x4. They're practically kind of equal because they have 4 components going across. So that's why we need to do that. That's kind of the reason why the fourth component is added there to begin with. Once we're done, once we have that, basically undoing the projection matrix. That's basically what we're doing the projection matrix in reverse. We're kind of like undoing it. We reset the z back to -1 because we want to reset its direction, and then we set the fourth component to not a 0. By using the fourth component, basically not applying translations like actual movement, it kind of negates it. That's what it kind of does when you're dealing with matrix math. So in the end, we end up getting kind of a direction vector instead of an actual point. So that's why we're setting this up. And so we go to the next step, and now this is where we're going to finally get, I guess, the world direction that we're pointing at. And we take our vector for I, and we multiply by our camera's local matrix. Remember, the thing says to do the inverted view, but the inverted view is the camera local matrix. The view matrix is the inverted local matrix. It's backwards. I guess you can say it's backwards the way I developed it, because that's what makes sense. Because the view matrix, in all honesty, is the local matrix inverted. So once that's done, then you just convert. You just take the first 3 components of the vec4 to make a vec3 out of it, and then you normalize. And now you have the direction. You basically have the direction based on the origin that the mouse clicked on. So if I clicked somewhere off to like top left corner, it's kind of like from the center screen to that corner. That's the direction vector that we are creating. But we're creating the direction vector in a frustrum direction. So we're kind of pointing at the other side of the cube, or the other side of the deformed cube with this vector once it's normalized. Once you have this direction, all you have to do is grab the camera position. Now, if you have a normal camera, like a third-person camera or a first-person camera, you can take the camera's position to do it. The camera I'm using right now is an orbit camera, so its position, it's kind of screwy in a way, but the way it creates the view matrix, that you can't actually get its real position from the orbit camera, but you can get its actual true position in the local matrix. And if you know where the matrices are, position 12, 13, 14 contains X, Y, Z. So after all the rotation matrices and everything else that's been applied to actually create an orbit, that's where we can actually get it. But if you're using a normal camera that follows regular transformation matrix, it does everything in the right order. Like 90% of the time, the camera you're using is normal camera, so you can use the position. But like I said, currently for fungi, I have an orbit camera, so this is the only way to get the actual position of the camera. So the race starts at the position of the camera, which is the center of the screen. So it's like I said, it's the origin. Then I take the ray, I multiply it by a value, because the ray is a normalized value, so it's everything is kind of between a value of 0 and 1. Or is it somewhere between -1 and 1, I think. Sorry. We'll multiply by 20. So this one gives me a range. So I can actually set a range of how far I want my ray to be. So the starting point is the center, and then using the ray that actually points to the other side of the frustrum, using that direction vector, increasing it by 20 units, and then adding it to the start. So, well, I'm actually not adding to the start. I'm actually cloning it. So I'm starting with the origin point, and then adding 20 units of distance in that specific direction that I'm looking at, and that creates our ray end. And then once you have our ray end, we have our start and end and then we kind of update. And this is the debug lines. And I actually, I actually think I forgot to mention that our debug lines is kind of broken. So I'm just going to quickly show you before I go to the demo. One of the first things is this was originally a class. Now it extends renderable. You added the mat, and then it has it calling the super. Commented this out because renderable actually has these values. And I think that might be it. That's only. Yep, that's it. Like it was broken, so I needed to convert it into renderable to make it work again. Because I've done so many changes, it's better off just extending the original object than kind of recreating it with class. There's like certain things that now exist in renderable that it's really required to use our rendering. So, all right, so that's the first way. So now if we go to the demo, and you can ignore this. Like I said, I'm making a floor plan editor, and the idea is the reason why I need the recasting is I want to be able to select a wall and move it around. So I need recasting. So I guess let me show you. If I click point here, point here, point here, point here, you don't see anything. But I think once you start rotating it, then you see the points, because all the points go to the origin except for one, and that one is the one that I kind of use to start clicking and dragging. So every time I click, I automatically create a raycast. So let's see, I want to point in that, right in the center of that wall. Click, and if I drag, and there it is. That's really where it is. And it starts off with a camera existed, and it ends 20 units away. And that's really the gist of it. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have all those points, and they all converge to the same spot. Because like I said, when we're creating that direction, it's the direction of the frustrum. So if you can actually see that frustrum being actually visualized now, because that's the center of the screen at the time when I was doing all the clicking. So when I was actually determining all the directions, those are all the directions being expanded out. Now that I have the frustrum backwards, now the point looks small and everything's big and so if I, there you go, you can kind of see it more. So that's really, so when we're looking at the screen, that's really what it looks like. And everything's at that point. So I did a bunch of scatters and then went to that one point. All right, so that was A. Now I'm going to go to B. I don't have to explain too much because it's almost identically the same thing. So, we're getting our normalized direction. We don't need an eye or anything. So the eye thing is right here. The original was defining, but now because I need to define two different ones because I want to go what's near and what's far. So basically, what's behind me, the furthest point in our cube space, and what's the furthest point in the other direction that I'm pointing at. So, all right. So one of the first things we're going to do is that before we do all this multiplication, is that we're going to create a matrix 4, and we're going to multiply our projection matrix and our inverted local matrix. This is our view matrix. So this is the stuff that requires us to reach device coordinates, coordinate system. So we're going to multiply them just like how we do with the shader. But since we want to go in reverse, once we have our world matrix, we do an invert. So now we're going backwards. we're going backwards. It's kind of like how we were doing it here, but we had it in the first way. We had to do them separate because the point, like the first time we multiply, we need this to be a 1, and the second time around, we need this to be a 0. That's because we were looking for direction. This time, we're not looking for direction. We're looking for the actual points of 3D space. Oops. So once we have the 3D, our world matrix, then we kind of start defining our near and far. And we just multiply or the world matrix by these 2 points. We have our mouse coordinates and then the 2 sides of our frustrum or cube or whatever you want to call it. Now, the magic trick to get this to work is that we do have to use the perspective divide. It's like this thing says, you kind of just normalize everything. And you normalize, so, we have our 4 points, right? These zeros now get filled in. And to do the perspective normal divide is that you take the 4th component and you divide it by the XYZ. So XYZ is divided by W. That's what we're doing in this point. And we do it for both. I have it commented out because I decided to just make a loop. So I just do a loop. It's done in 4 lines of code. The end. Now that you've normalized the points, basically, you kind of you convert them in a certain way. You can then create the near and far. Actually, they're points. They're not rays, but whatever. They're just points. The near point is the actual point on the screen in 3D space. It's not a direction. It's the actual point. So if I poke here, that is the actual point I am doing. So like I said, that's really all it is. This actually is less code than this one, to be honest. This one it's a lot more work to get it done. But the advantage of this method is that you can actually create a range, which is kind of useful. Like if you want to, I guess if you're doing a first person thing and you only want to be able to select something, or like let's say a door, you can only touch a door if it's like 5 units away from your position, or like 2 units away. By doing this raycast, you can always point in front of you, or point wherever the camera is pointing, and if something's within 5 units away, and you'll say it's a door, then you can unopen it. If the door is 20 units away, it'll never show up because you set the ray range to be only 5 units. So this method of going about it makes it quick and easy to use the multiplication or to create a range for it. The only difference is that the range is then kind of based on the center of your screen. Like I said, where the second method, it actually creates the actual 2 points on the screen, but on both sides, like of the frustrum. I guess you'll see in a minute. And what else? But like now, this one does not create a range. Now, can you create a range? You can, because if you take far and subtract near, you will get a distance, a difference, an offset. And then if you normalize it, at that point, you then create a direction, because a direction is a difference of 2 points in space. So now, if you do a subtraction, that means now and then you normalize that subtraction, you have a direction. Then you take that direction and again, you multiply it by the range that you want to go. And then you apply that range to array near, which is the actual point that you actually picked in 3D space. And so with a couple extra bits of code, you can do that. So like if you want to like make this into a direction, I guess something along the ways of ray far minus ray near You normalize it, and then you multiply it by range. Range, and then you add it to ray near, which is the origin. So so basically you would have to do this to take this method, but to create a range out of it. So this is pseudocode. It doesn't actually work. You kind of have to do this part. If this was C++, it would be that easy. But JavaScript doesn't allow me to program operators. So so I just wanted to quickly say you can use this method and get the benefit of creating a range. You just got to take that extra step to generate the direction. That's all. So save. If I come back here, refresh, we're going to be using the second method. So if I click, let me do it this way because you can probably see it better. Now, if you notice, the points are no longer on the center. Those are the actual true points that I clicked on in 3D space when the camera was there. So that point is then pointing to the exact opposite on the other side of the frustrum. And it's kind of funny that that's how far it goes. I guess that's as far as the viewing range goes. I guess so, because usually it goes as far as clipping space. So it goes like to the very end. It looks like it doesn't because the grid is there, but since it's below, it's probably, yeah, it does extend. So if I start panning over, so that is the edge of the wall. This is really the end of our 3D space. So that's why we use the camera to move the whole world to be visible within that cube that's 2 units big. That's why the origin is 0, 0, and then each direction it goes by 1. So, whoa, the camera's not all out of whack. All right. So, and it still works. If let's say I want to point in that, it does go through there. If I want to point here, it does go through there. So, either method, I guess, would work. I guess method B has less code. Most often, if you are doing some kind of weird collision, or like especially a mouse collision, like I just so if I want to do like in this case, the second method makes more sense because I'm actually going to do an intersection comparison throughout the entire cube space. So I don't have to the range doesn't matter to me. I just want the entire cube space, and I want to measure or find out what it intersects. And that part will be in part of another video whenever I get to it. But I wanted just to be able to show you the mathematics around recasting from the mouse click on the canvas, and then how to visualize it. So you can kind of see where everything is when you click on it. So this way you can kind of really visually debug what's going on. So there you go. So I hope you learning some cool things. I hope I explained it. The idea they have 2 different methods to go about it. You know, like I said, one goes by points and the other one goes by direction. You're depending on how you're calculating it. And either way, you can do direction, and I don't know, you can go crazy. So I'm just shooting rays all over the place. I wonder if this can make for an interesting game if you think about it. You know, like you start every time you click somewhere, you got a ray, and you know you maybe have a character that has to avoid it, or go around the rays. I don't know. I have no clue. But yeah, this is recasting. Pretty simple. And this is my floor plan application, which right now so far I only have the ability to build custom walls and with code lay them out. Everything's built on a special grid. The grid looks different because I built the grid from scratch again. So this is a new grid object, which I kind of like the look of it. It's lighter, and I can kind of see where the X and Z positions are. Because this is so I know where origin is. Yeah, I don't really want to go too much into detail about the floor plan because I'm really not expecting to write videos about how to build this. This is going to be probably an open source thing I'm just going to leave out there. I just want to build this tool because there's a lot of things I can learn from it, like recasting, intersections, collision. I might do like a collision. It's like maybe I have a little ball that I can kind of use a camera controller to move around. So yeah, I can do a lot with something like this, and it can end up being like a very simple level editor. If a lot of people really want to know how this works, maybe I will make a video showing how I'm slowly building up this thing. But for now, I'm only going to use this as to teach certain fundamental pieces of 3D programming and certain things that you need for game or web for applications. Where the other videos that deals with fungi is mostly toward video game development. This I'm actually going toward more application development because I really want to do both. I actually want fungi to function for both. I want it to be both an application development platform and a game development. And I don't want to bog down application stuff with a bunch of game things that aren't needed. So I kind of have to balance how the libraries are built. So this way I can say, well, you can exclude these extra libraries because this is really only game related. And if you're building an application, like you don't need a physics engine. So like I would like the physics engine to be independent of the graphics engine. So things like that. It'll be a long while before I get to the physics engine. I'm kind of hoping maybe I don't have to do one, but I'd probably have to do like a very simple one. But yeah, so that's it. I hope you guys enjoyed this. Hopefully I made a recasting a little bit easier. Like I said, it's kind of hard to find a really good, simple example of recasting online. Something I can kind of take apart and look. That's what took me so long to really figure it out. But now that I think this would be a great starting point for anyone who wants just to learn it. Because like I said, I made a very simple function. You can just download this from GitHub, and you can play around with it. And like I said, you can visually see all your recasts. If you want to take this and then add extra objects on the screen to experiment with intersections, like with planes and spheres and cubes and whatnot, go for it. Because I'm probably gonna get to that point. At some point, I'm gonna do an intersection. Next video you might see related to this would be when I click on this, it finds an intersection, and then highlights the wall. So that would be like the next step, is really just scanning all the walls and figuring out which wall is the closest that gets clicked on. Because I can have because you have to kind of have to realize I can do something like this, and it actually ends up intersecting two walls. So I got to make sure that even though I'm looking through, I have to search all of them, but I have to find which one is the closest. So that means I actually clicked on that one, not that one. So I got to work that out, and that'd be like probably the next thing related to recasting that I do, which I hope I think you guys probably will really love, because just be able to create the rays was a challenge, but now using the rays are going to be an extra challenge. So that's it. Hope you enjoy. Hope you have fun. See you guys at the next lesson. Don't forget, like, subscribe. questions. I try to answer all you guys. Thanks a lot for watching. Bye.